to today's webinar on how to suppress the penetration of molten cast iron into sand mold. I think this is our webinar number 10 in our series of webinar that will maybe end with around 35 webinars. And this is in one of our modules. It is webinar number 3. And so you are most welcome. And we are so happy that you found your way here. And here you see the list of the registrants, quite a lot from Sweden today, and dominated by Scania, I think. You are quite welcome, but also to the other ones. And especially welcome to those from abroad. Not as many today, but nice to see the diversity attending our webinar. And as you may already know, this is one of our webinar in our series called Metal and Polymer Component Manufacturing, which is addressing those industries, also helping to raise the competence level in a quick, fast way and easy accessible for you as well with these short webinars, and hopefully preparing you better for recovery when the crisis is over. And we are seeing the end now, luckily. And I hope you all are, wherever you are out there. And me speaking is Stefan Brolin, working here at the School of Engineering. And my colleague, Ehsan Ghasemali, you will meet later on. We are moderating today. Ehsan is also the project manager of the Weblon project. But our main characters of today, of course, our presenter. We have Associate Professor Taishi Matsushita and introducing the subject, and then we will also listen to Assistant Professor Joseph Swidro and Professor Attila Dioshegi, all from the School of Engineering. So this will be interesting today. And if you mind clicking the next, thank you. The agenda for today, we are just starting the presentations within a minute. And for 45 minutes, we will listen to the presenters on the subject, and then we will go into breakout rooms for group discussions. And then there will be a wrap up within 1.5 hours. So please have your microphones turned off during the meeting unless you are the one talking, so there won't be any background noises hearing through. If you have questions during the presentations, which are mostly welcome, do write them in the chat, and we will address those towards the end of each presentation or at the end of the webinar. And please be active in our group discussions, as those are an important part where you can give input and where we can share ideas. So if you don't want to be seen online as we record this one, and it will be available to you afterwards, please turn off your camera. But the breakout rooms will be deleted from the recording, so please put on your cameras there for having more pleasant conversations. And just as a reminder, you will get the video afterward, or a link to the video, and you will also get the PowerPoint presentations. So there is no need for taking notes. And if you, for any reason, are unfamiliar with Zoom, down to the left, you have the microphone on and off and video on and off. And a bit to the right, you have the chat button, which open a chat box where you can either choose to write the questions to everyone, never mind, or you address them to me. That is Stefan Brolin, probably the only Stefan in the list there. And by that, I hand over to Taishi to start the presentation. Welcome again. Your microphone is off, Taishi.
Yes, yeah.
Oh, good.
I think everybody can hear me. Can you hear me?
Yes.
Yes, thanks. Good morning, everybody. My name is Taishi Matsushita, and I'll give the first presentation. Let me show the. Yes. And I'll talk about the penetration theory and the guideline to suppress the penetration. But if I say theory, you might be scared, but don't worry. It's a very simple one. And it's not just boring mathematics, but we can derive useful information to create a guideline to suppress the penetration. So we'll see the penetration theory, and we'll go through the guideline to suppress the penetration. But if I start from the theory, you might feel it's boring. So I'll start the X-ray image of the penetration behavior. So by using the X-ray apparatus, we can do the in situ observation of the penetration behavior. For example, here is a typical X-ray image. Here we have a porous media, which corresponds to sand mold. And here, this dark part is a penetrated molten metal. And it's penetrating from the bottom in this case. Here is the bulk of the metal, and here is the interface between the porous refractory and penetrating molten metal here. So first, I'll show you, by the way, yeah, we can observe such a penetration behavior by using the X-ray apparatus, which you can find at the hospital, that kind of Röntgen apparatus to check your body by using it together with furnace. And this is a schematic illustration. And I'll show you some video clips which shows the penetration behavior. First example is the penetration of molten mercury at room temperature. Mercury is, as you know, the molten state at room temperature. And if I start, let me start the video clip. Just a moment. Yes. Here it doesn't matter. Yes, here, for example, here there is a cylindrical shaped refractory porous sample. And here is the bulk part of the metal, mercury. And here is the interface between molten metal and porous media. And this part is the penetrated molten mercury. So we'll see how it's penetrated into the porous media. So like this. You see, the molten metal will penetrate after we apply the pressure. We need a certain external pressure to penetrate the molten metal. And then you see here, it's a molten metal is choosing, now the pressure is increased. And of course, the penetration depth will become deeper. Now the pressure is applied. And as you can see, the molten metal is choosing the larger pore. So it can easily penetrate into the larger pore, but not smaller pores. And the next example is the silver, molten silver at 1000 degrees Celsius. It's somewhat similar. Here we have the cylindrical shaped porous media. And here, this dark part is the molten silver. And here is the interface between metal and porous media. And now it's slightly penetrated into the porous media here, as you can see, at lower pressure. This. And if we increase the pressure, then it will penetrate further. And now the pressure is increased. Then here is a penetrated molten metal, and after we apply the pressure, the penetration takes place again like this. And again, it's choosing the larger pores. And the third example is the molten steel at 1600 degrees Celsius. We'll see it here in this image. Here we have the porous refractory sample. And here is the interface between the molten steel and the porous refractory. And this dark part is the penetrated molten steel. And this gray part is just a shadow of the porous media sample. So it's already penetrated up to this height. And then the penetration, yes, you see here, it's penetrating here now. And then penetration is stopped. But after a while, the penetration will start again. If you say, I think it's near here, if you see this region, now its penetration is stopped. But we will see, yes, now it's penetrated to here. So sometimes it goes to down if we have the larger pores to downwards. This is a penetration behavior of molten metals. And from these observations, for example, we can plot the maximum penetration height against the applied pressure, external pressure. Then we will see this type of two stages. So at a relatively lower pressure range, the penetration is somehow suppressed. So the slope is small, but above a certain pressure, the slope will become steep like this. So there are two stages, we can say. And these results can be analyzed by using the capillary model. But before we go to the capillary model, let me explain the contact angle in case you don't know about the contact angle. I believe most of you know it, but this is an important parameter to discuss the penetration behavior. For example, if we put a droplet, water droplet on a glass substrate, for example, then droplet shape will become like this. And here, the angle between this substrate, the solid part, and the wet part is called contact angle. So in this case, the contact angle is smaller than 90 degrees. But if the droplet shape becomes like this, then we have the contact angle larger than 90 degrees. And we can find a similar angle in the capillary tube as well. As you know, in the capillary, the meniscus will be formed like this, for example. Then here you can find the contact angle. And in the case of, for example, combination of mercury and glass tube, then the meniscus shape will become like this. So in this case, the contact angle is larger than 90 degrees. So this is the contact angle. And now we'll go to the capillary model, the theoretical part of the penetration behavior. And here is the basic here is the basic equation of the capillary model. So the penetration speed, V, is described as a function of radius of capillary and the viscosity of the penetrating metal and the penetration height and the pressure balance at the penetration front. And this equation is suggested by Washburn. So it's called Washburn's equation. And it's literally suggested hundreds of years ago, but it's a very useful equation and it's widely used. And there is no flaws about this equation. So it's widely used and reliable equation. So based on this equation, yes, we can consider this pressure balance in our case. We'll focus on the system which contact angle is larger than 90 degrees, since in the case of oxide and molten metal case, the contact angle is higher than 90 degrees. So the force balance at the penetrating front will become like this. So we have the applied pressure, external pressure. For example, in the case of casting, it's correspond to the metallostatic pressure and so on. And here we are considering the penetration to upwards. So we have the force due to the acceleration due to the gravity here, this term, and we have capillary force. In this case, the contact angle is larger than 90 degrees. So the capillary force is acting to downwards here. So here is the capillary force. And then we can derive the maximum penetration height by putting this velocity is equal to 0, since at maximum penetration height, the velocity is 0. Then simply we can describe the maximum penetration height as a function of external pressure, surface tension of metal, contact angle, density rho, and acceleration due to the gravity g, and capillary radius r. So this is the basic equation to analyze the penetration behavior. And actually, the penetration will take place very quickly. Here is an example of the calculation. Here, x-axis is the penetration time, and y-axis is the penetration height, and it's calculated based on that Washburn equation. And as you can see, within 1 second or even 4.5 seconds, the penetration height will reach almost maximum. So I can say the penetration takes place almost immediately. And now I talked about the penetration to upwards, but we can use the same type of equation for the different direction as well. So for example, I don't go to the details, but for example, for the penetration for the horizontal direction, we can simply neglect this gravity term. And if the contact angle is smaller than 90 degrees, then simply the direction of the capillary force is reversed like this. So we can use the same type of the same equation for the different cases. So again, I will come back to this graph. So here, in the stage 2, so it means relatively higher pressure range, we can use this equation directly. But in the case of stage 1, relatively lower pressure range, we need to put this correction factor C. And this correction factor is known as the tortuosity or labyrinth factor. We have to use this factor for the lower pressure range because in the capillary model, the penetration takes place straightforward. We assume the straight capillary, but in reality, the pore shape or pore path, the path of the pore zigzag has a zigzag shape. So we have to correct this influence. If we go to the higher pressure range, then the molten metal can penetrate to the smallest pores as well. So it can penetrate almost straight forward. So we don't need this correction factor, but at lower pressure range, the molten metal will choose the larger pores. So its path goes through the zigzag path. So we need this correction factor. So this is a basic equation, but from these equations, we can derive some useful information actually. For example, if we consider the surface defects, we want to suppress the initial penetration. So it means we want to achieve this H max is less than 0, so there is no penetration. And according to the equation, the maximum penetration height will be described with this. Then we can say to suppress this penetration height, we have to decrease this, we have to increase the surface tension, sigma, since this term has a negative value. So if we could make this absolute value is larger, then we can suppress the penetration. Here, we are considering the contact angle is larger than 90 degrees. So cosine theta has a negative value, okay? So we can try to increase the surface tension sigma by decreasing the amount of surface active elements such as oxygen, sulfur, and so on. And we can try to increase the contact angle theta so that this term becomes larger to the negative side. Or we can try to decrease the pore size R. And on this term, in this term, we can try to decrease the external pressure, such as metallostatic pressure. Then metal penetration will be suppressed. And even if the penetration starts, we can still try to suppress the penetration depths. It's almost same strategy, but again, we can try to decrease the pressure at the interface, and we can try to increase the contact angle between the metal and sand or grains, mainly silica grain. Or we can try to make the correction factor tortuosity smaller, so by creating the labyrinth in the sand mold. Or we can try to slow the penetration speed. Then the penetration will be stopped by the solidification before it reaches that maximum penetration depth. And the last point is we can try to smaller the minimum pore size, for example, by creating some by the reaction product layer and so on, so that we can block this. So we'll go through the details, some details quickly. So first point is, yes, once again, we can try to decrease pressure at the interface by decreasing the metallostatic pressure. And we can try to increase the contact angle between the metal and the sand particle by addition, for example, by creating the reaction product layer, which has a higher contact angle. And here is an example of the contact angle of the different oxide materials. So if we see this graph, then we can say the barium oxide has the highest contact angle. On the other hand, the silica is here, yes. So if we consider it from the penetration viewpoint, then barium oxide is desirable. And it's also known that in general, the contact angle increased with decreasing of temperature. So it means the lower boiling temperature is desired if we see it from the penetration viewpoint. And the third point is to decrease this, to suppress the penetration in the stage 1 by creating this lower labyrinth factor. I think it's possible to do something by just optimizing the particle size distribution as well, such things. And the fourth point is, again, it's related to the contact angle. And you see, in the initial stage, we may have higher contact angle, but with time, the contact angle might be decreased. Then, even if the penetration is stopped at this point, the penetration will proceed further due to the decreasing of contact angle. So we want to avoid this drop of the contact angle. So again, barium oxide is better in these oxides, since it's the degree of the dropping is less compared with the other cases. So such things we can find out. And the last point is we can try to close or make it smaller, this pore. Then we can shift this critical point to the higher pressure range. We can extend this stage 1 to the higher pressure range. Yes, this was my presentation. Sorry, I know it was very quick due to the lack of time, but that was my presentation. Yeah, thank you.
Thank you, Taishi. There are actually no questions in the chat so far, so we can hand over to Joseph.
Yeah, we'll discuss it in the breakout room. Yes.
Yeah, thank you. Now we can shift a bit towards more practical things. And I will talk about step cone test castings, which is a quite prevalent tool or casting used both in industry and both in research activities. It might be familiar to some of you working in the industry, and it's quite known in research. And during the first couple of minutes of mine, I will show you how to use step cone castings, why it is a great tool, and I will try to explain it through a case study we have made before. So next, please. So penetration defects are a big problem. They are showing up in industry, and everybody knows, and we all know that we have to deal with it, and we have to find our best approach to have a solving for that. And using step cone castings, I believe it's a great tool at least get to know what we are facing and make the right approach to penetration defects. Next. So the step cone castings, or as might say, as we might say, stage cylindrical test castings, looks like this, as shown in the picture. So it has an internal geometry with different steps, and the internal geometry is usually produced by using an internal core, and then we can achieve these different kinds of steps, starting from the bottom with the thicker wall thickness of the casting and going up even thinner up to the top of the casting. And the good thing with that is that we can achieve different heat load environments when it comes to the molding material. And here in the picture, I show some alternative gating system, which is well working. We have tried it, but of course there are alternative ways how to cast this step cone casting. Next one. So during this case study, we have picked sulfur as the focus, because sulfur is an element which is surface active. It can influence the surface tension of the molten metal. So it's quite interesting what sulfur can do to the penetration and how it helps or not help penetration. And other important thing is about sulfur that it is included in some of the molding materials. For example, furan sand have a moderate amount of sulfur depending on the catalyst we use. It can be sulfuric acid as catalyst. So there can be local buildups when it comes to sulfur, and it can be an important factor when it comes to penetration in that case. So we prepared the mold for this step cone casting. We use green sand to make the outer surface of the casting for the mold. And for the internal core, which makes the steps inside the castings, we use the regenerated sand, 90%, 10% was new silica sand. And we use furan resin and phosphoric acid catalyst. And when it comes to the addition of sulfur, we try to oversaturate the system with sulfur at one point to get very harsh reactions. And therefore we came up to add a quite amount of sulfur powder mixed in the sand before making the core. So we added 2% of sulfur powder to the core material, which might sound a bit more hard because that's a lot of sulfur, but in the first place, as I said, we wanted to see the effect on the big picture. Then the casting was cured by gray cast iron, hypoatomic gray cast iron, and the curing temperature was used 1380 centigrade degrees. Yes, next. And then we had the casting. We separated two halves, and as we just look at the casting, we already see that there are some wide fracture carbidic layer came up in the metal core interface, basically on each steps, regardless of the wall thickness of the casting. And of course, we wanted to know more about this wide fracture layer, so we made some microsection on the down left, which contains all the steps. It was a quite challenge to make this kind of microsection in this size, but we managed to do it. And as I said, stage 7 from the bottom is the thickest when it comes to casting, and if we go up to stage 1, there we have the thin casting wall compared to others. And then we made some etching Next. And we use an optical microscope to measure the thickness of this white fracture layer stage by stage. Here in the picture, you see stage 3, 4, 5, and 6. So the middle part of the casting. And we made 4 measuring points by optical microscope software. And then we started to relate the thickness of the white fracture layer to the wall thickness of the core or the casting, sorry. Next. And then if you see the first table, we have found out that the thickness of this white fracture layer is decreasing as we have thicker and thicker wall thickness in the casting. So in the bottom picture, we can see how the white fracture layer thickness is related to the wall thickness of the casting. Of course, it's not only the wall thickness of the casting. It might be it has something to do with the metallistic pressure, because it will be higher in the lower parts of the casting and decreasing upwards. But it was quite interesting that the relation is quite straightforward when it comes to these features. Next. Then, of course, we would like to go further, and of course, we need to look after the sulfur. So we use this microsection, and we just picked one stage. I think it was stage number 5. So as you can see on the picture, in the roughly the middle section of the casting, and we made the electron microscope and microprobe examination. And what we saw on the microscope picture is that we can differentiate different areas when it comes to the surface area of the casting. So if we coming from the direction of the mold, we have found the white fracture carbonic zone, which was prevalent even with bare eyes. Then in number 2, we have a relatively thin zone of degenerated flake graphite, which is not that significant, but still there. And then if we go further, we found the basic matrix, the original matrix with the flake graphite. And it's kind of interesting that there is a relatively hard shift between the carbonic zone and the basic matrix. But as I said, we were looking for the sulfur. Next, please. And using these points 1, 2, and 3 from the previous picture, we made the microprobe test looking for the sulfur. And we have found out that on the first picture, the distance from the metal core interface is quite low. So if we are in the carbonic zone, there we have a quite high amount of sulfur, 2.2%. Then if we go further, in the transaction area, we have a slightly lower sulfur content, and quite good distance from the metal mold interface. So in the basic matrix, we have measured 0.51% sulfur. Next, please. And this means that we have discovered that the sulfur content will decrease depending on the distance from the metal core interface. And this is the relation between the sulfur content and the metal core interface distance. So the sulfur content is slightly decreasing at a certain point. Next, please. So as a conclusion, due to increased sulfur level, which we made up artificially, the depth of penetration defects increase. By depth of penetration, I mean, in this case, it was a solidification anomaly occurred during the forming of the surface shell in the gray iron casting. And in this case, a more definite sulfur content changing was noticeable when we shift towards the metal core interface area, and this sulfur content were decreasing from the interface to the basic matrix of the casting. And we have also made a case study on ductile iron. It behaves completely different way, but we have chosen to show you this gray iron case study. Okay, thank you for your attention. And I think we have some questions.
We actually have a questions there. I think we have time to take it. What is the nature of the carbides appeared in the metal core area?
Yeah, we haven't made more deep analysis when it comes to nature of carbides. We just identified it, but I think we still have the microsections, so I think we can make a more deep analysis when it comes to nature of carbides. But the scope of the study was in the first place to identify what we have in the beginning.
Thank you. That's a topic for next project then.
Yeah, yes.
Thank you, Josef.
Thank you.
Your last picture, wasn't it?
Yeah, I have a thank you slide, yes.
Okay.
But thank you again then.
And there you see the contact details. And by that, we hand over to Attila.
Yes, you. Hello, everyone. I'm going to end this series of presentations related to penetration. My intention is to give you information about the penetration chronology in lamellar cast iron. It's a more practical issue and could have some influence for you who are practicing in foundries and try to understand how and when the penetration appeared. I'm going out from a very complex shape, cylinder head, produced in hypotectic gray iron and formed in a green sand mold, and organic bonded cores are used internally, and you can see the extremely complexity inside the casting. And why we are talking about chronology is because in such complex shaped castings, we can find different type of penetration, and it will be interesting to see which of them appear earlier or later, or what could be the mechanism behind initiating the penetration. We have identified, or we all know, that there are two major type of penetration you can find in such complex shape casting. The one is the crack appearing in the mold, and the metal is filling this crack, and on foundry language we call it rat tail. And then we have the traditional intergranular penetration, where metal is penetrating into the interstices between the sand grains. Talking about rat tail and the crack, it can be observed two different type of cracks or metals penetrated into the crack, and the one and based on the morphology, on the microstructure, which is presented in these two pictures, we can distinguish the time for the metal entering the space with use of color etching. In the upper case, we see an early present penetration into the crack, and what we can see, the morphology of the metal is solidifying according to the metastable diagram and form carbides. This indicates that it is an early penetration when the mold material is still is cold and have a good ability to cool down fast the liquid metal. In the lower picture, you can see example on late penetration into the crack, and the reason is, or the reason, the evidence comes from the morphology observed in these cracks, where you have a normal gray penetration, including all the required phases in a lamellar cast iron, including lamellas or graphite lamellas, including eutectic cells. So it indicates that it's slow solidification, and this indicates that this must happen late when the sand temperature was quite high and contribute normal or slow solidification. Talking about the intergranular penetration, even here we can observe different morphologies. In the right side, you can see droplets found behind the metal mold interface between the sand grains, and in some cases, the observed morphology of the gray cast iron alloy include all the expected phases, like the primary austenite in the middle in this case, and the eutectic phase, including the graphite lamellas. And the expected phenomena is that the metal has been squeezed between the sand grains, and this is expected to be a penetration from the original bark material with the original composition, which was a hypoeutectic composition, and we call it a suppressed solidification penetration. It means that the penetration started quite early, before the solidification start in the bark material in the casting. The second type of penetration is the metal expansion penetration, and in those cases, the droplets found between the sand grains contains only pure graphite austenite eutectic phase, and this is associated with the metal expansion penetration at the later stage of the solidification, when a part of the structure have been formed, the primary phase exists, and the remaining liquid phase have been segregated to an eutectic composition and was squeezed in between the grains. In the next slides, I'm going to explain the physics behind this phenomenon. On the left side, you can see the phase diagram for a two-person silica iron carbon alloy. And on the right side, we can see the density variation diagram for this given alloy, which is a hypertectic composition. The expected density in the liquid state is expecting to increase due to the decrease of the liquid temperature until the solidification starts at the liquidus temperature. There start the primary phase to form, and the density curve became sharper due to that dense phase is precipitated from the liquid. And this happens until the temperature and the composition reach an eutectic temperature and eutectic composition, when the carbon precipitate and form graphite, and due to the graphite formation, which is a light phase, the density of the composite of the cast iron will decrease until all graphite is or until the eutectic solidification ended. Of course, the graphite continued to precipitate in a smaller amount, but the density variation will be dominated by the shrinkage of the austenitic phase, and then we can observe another density variation around the solid state transformation, but that is not important for our reason. Back to the observations, then we can see that normal composition penetrated during the liquid domain from the casting into between the sand grains, then forms a microstructure, which is a structure including all the type of phases, primary and eutectic. And then the second one is a phase which can be formed only if the penetration happens late during the solidification, when the composition of the liquid has reached the eutectic composition. So more cases can be seen in these pictures, where a complex shaped sample is cast and it has an internal core. It's important to emphasize that this convex mold surface is in complex shaped castings used to be the place where we have the hot spot of the domain, which makes that the solidification became so difficult, or the solidification here you have a late solidification compared to the rest of the casting, and when the conditions are not good enough, that the metal squeezed out from the or due to the metal squeezed out from the bark to penetrate in between the sand grains, then the whole surface will be pushed away. And what you can see here is the metal squeezed out, remove or push back the surface of the sand. And the drawing force is the graphite expansion, of course. We have another interesting case, which you may seen in your foundries, is that when the metal surface, the casting skin, is not permeable due to metallurgical conditions, you have an early form casting skin, then the graphite expansion can not anymore squeeze the liquid matter through this skin. And in that case, what will happen is that the casting skin becomes bulged. For the colleagues in Swedish foundries, I can name the expression formtagning is the right expression. So just last picture where I would like to show how it was demonstrated, this metal expansion penetration. Most of you knows the quick cups used, and this is a quick cup which is modified, and it's a sand core introduced to create a critical area for penetration. And we have in the quick cup a thermocouple, a normal thermocouple, which is soldered, and it is somewhere in the middle of this road. And additionally, it has been in a thermocouple, which is open, area is, and is closed. Then after filling up the cup with metal, then those who are familiar with the cooling curve of a quick cup, you can see the registered temperature variation with a primary phase and eutectic phase solidification, and to the end of the solidification shown by the red lines. And the open thermocouple will show wrong values during the recording process until this point when the penetration happens, and the thermocouple circuit will be closed due to the penetrated metal, and it starts to measure somewhere in the middle of the eutectic reaction, demonstrating that the penetration happens at this moment. So finally, I would like to conclude that several types of penetration defects can be found in a single complex shape casting. The various pressure forces can be observed in initiating penetration, both static pressure and expansion pressure. Metal expansion penetration can squeeze both droplets between the grains, or complete layer of metal will offset the sand grains. When the surface is not permeable, the whole casting skin becomes bulged. And finally, the color etching can be used successfully to decide the chronology of the penetration formation. If you are wondering how to apply color etching, or what is the tricks to perform color etching in your foundries, you are asked to look after our next webinar within the series for cast iron and ferrous alloys. It will be before this summer, when during the whole webinar we are going to talk about color etching. So with this, I would like to thank you for your attention. And give back the words to the moderator.
Thank you very much, Attila, and also other presenters, Taishi and Joseph. It was a very nice combination of theory and practice, at least to me, and I personally learned a lot. Thanks for the presentation, and I hope it was enjoyable for the participants as well. As far as I can see, there's no questions in the chat for the presenters, so we can move to the next step. As we also tried, as Stefan also tried to mention, we would like our webinars to be more interactive. We do not like it to be one way, and we want for you to be a platform where you can discuss deeper questions, which normally leads to new collaboration, new ideas to do something together. So in a short while, I will create 2 or 3 breakout rooms where you can join yourself and discuss either questions that you had from the presentation or the questions that we also presented here. I try to read it for you. If you are a foundry process or quality engineer or supplier of sand coating materials or such, what kind of advices do you give to suppress the penetration of metal into the sand mold? And the other question, which would be interesting to discuss, what actions or in-house tests your company may conduct to troubleshoot and predict penetration-related defects. If there are other questions that you're interested to discuss, you're more than welcome to ask in the discussion group. So we will have around 15 to 20 minutes where we can discuss these questions or other questions. Stefan is also sending you the questions in the chat. And also to make the discussion ongoing even after the webinar, we have created a link in Padlet where you see, this is the screenshot of the website where you see these questions and you have the opportunity to continue the discussion even after the webinar. We also put all the presentation file and recorded video later on in this link, and we will send you the link later on. So you're welcome to discuss, and after 15 to 20 minutes, we come back to this main room, try to wrap up, and hopefully by 11:30, we end this webinar.